Okay, so the paper I want to share today, linking to our multimodal learning topic, is an interesting application of deep learning modeling in media research. And the title is Diffusion of Multimodal Features for Social Media Retweet Time Prediction. So there are a lot of existing research on network analysis, user behaviors, and information propagation on Twitter. And regarding the retweet behavior, which is a very specific affordance on Twitter and many social media platforms. This paper comes in to fill in the research gap that many studies have overlooked the retweet time. So previous studies usually take a global network perspective, predicting the popularity of tweets or identifying retweeters just based on the entire social network. And their task is largely binary classification, like whether a tweet from others will be retweeted or not. But this study looks at the micro level of individual retweet behavior and predicting their retweet time. And that's a local perspective and multi-classification tasking essentially. So the author claimed that their approach is non-trivial for several reasons. And the first is that retweet time prediction has practical implications on sales marketing for better advertisement allocation for optimal exposure and influence. And the prediction can also be extended to measure the overall trend of information spreading, which is often of great interest to advertisers, policymakers, and some media companies. So here comes the model training part. The paper proposed an end-to-end deep learning model called Deep Fusion of Multimodal Features. It's short as DFMF. It combines three models of data, the content of the tweet itself, the social relationships, and posting time. So essentially, the task can be formalized by satisfying a mapping function that maps a tweet, the author and its follower, and the retweet time T to a predefined retweet time gap category. And the challenging part of this study is to overcome the complexity of information entanglement in social media and the difficulty to extract meaningful semantics from short and often noisy textual tweets. So this is the diffusion architecture where it involves three-part feature extraction. So for the tweet content, they first train word embeddings based on the entire collection of Twitter dataset. And then they use word2vec to learn the word embeddings for each word and finally produce a vector representation for each tweet. And the social network input requires node embedding, and they use an unsupervised learning algorithm node2vec to learn the hidden embeddings of each user in the network, and then generate a node vector represents all the users and followers. And the tweet posting time was transformed by a one-hot encoder to generate a time vector and concatenate it with the other two vector representation of the features. So with these new feature vectors, you just stack a deep densely connected layers on top of it with a redo function. Activation function. It can be formalized as this first function where the plus sign denotes the concatenation between multimodal features. And after that, you apply a softmax layer to compute the probability distribution of the retweet time. And also they choose to use cross entropy as the loss function for this multi-class classification problem. So a DFMF model has four different strategies for tweet encoding. So the study trained four of its variants for tweet encoding and compared them with the two baseline models. One is logistic regression and the other is support vector machine. And they evaluate the performance based on the precision, recall, and F1 score as shown in the figure. So from this table, the AV variant achieves the best performance overall among all methods with a precision of 42%, a recall of 48, and a F1 score of 41%. So it outperforms baseline method, the support vector machine, by almost 10% on average and slightly higher than the other three deep learning models across all metrics. So building on this multi-modal fusion model for retweet time prediction, I see some promising opportunities to enhance it further. And like the one key addition is to integrate topic modeling to classify retweet times across different topics. And this would allow for a more fine-grained analysis beyond just predicting time categories. And it helps to identify which topics spread faster and how engagement varies across them. And another potential extension is to use retweet patterns to detect ideological echo chambers. And the network embedding approach employed here can effectively map tweet diffusion among communities, enabling an analysis of how retweet time differ between like-minded interactions and cross-ideological exchanges. That's it.